So we start talking about pressure here, and our biggest use for pressure is just the inversion, where we're going to use pressure to calculate force, which is our old friend. If you multiply the pressure by the area it acts upon, you'll get a force. What is the direction of that force? Well, it's always such that whatever is causing the pressure wants to increase volume. It wants to get into a space that it's not already in. So there's no hard and fast rule. It's not always left, it's not always right, it's not always inward, it's not always outward. It's always such as the stuff that's causing the pressure wants to get in somewhere that it's not already, and if it can't get in there, it instead exerts a pressure. So for instance, if I had air over here at pressure P1, and I have some kind of barrier where it can't go over there, when those air molecules go over there, they bounce off, they get turned away, and they will exert a force. So since they can't go that way, they exert a force. The air molecules get a rebounding force, and of course Newton's third law says that if the air molecule gets bounced and turned around, then it'll exert an equal and opposite force forward on the wall. And then likewise, over here, let's say there's also air over here with some other pressure. That wants to get over here. Since it can't, it gets turned around, and in the process exerts a force this way. So notice that both pressures work to exert a force so that they could increase volume. So basically the force points towards where they want to go but can't go. And this ultimately is often the case that we have a competition of pressures on both sides. And so the overall force would just be the difference in the two. I won't worry too much about signs at the moment. And since they're acting on a common area, I might as well pull that out. So it's going to end up being a competition between the pressures. Okay? That right there is basically at the heart of our entire fluids unit. So we're going to flip that idea every which way. Okay? Notice that the way that it's going to go is that whichever one of these pressures is bigger, that's the pressure that wins. So in this case, I've drawn P1 to be bigger, and so the force overall, F net, is going to point in this direction. I guess I can call this F net here. So the operative thing that I want you to notice is that the net force always points towards the lower pressure. That's the takeaway of this equation. This idea that when you have a competition of pressures, the big pressure wins, gets its way, the smaller pressure loses, and so the net force will point away from the big pressure and towards the smaller pressure. We're going to do a lot with this. This will allow us to calculate something called hydrostatic pressure, the hydrostatic pressure equation. So you probably already know that when you go deeper and deeper into the ocean or a lake, the pressure builds. We can actually calculate with this idea exactly what that equation is. I can also calculate for you the operating principles of a barometer. So you may know a barometer is something that it can measure pressure. It uses this formula. We can talk about something called buoyancy. So why do things float or not float? That's all coming from this equation. And then, as we usually have to track with our previous progression, we're going to flip from forces up to the energy method. So we can also treat this idea in the context of energy instead, and we get to something called Bernoulli's principle. That's important for lots of applications. Fluid flow, and in your case, probably most interest, blood flow. So we'll be talking about that as well. So that pretty much is most of the rest of our fluids unit. In fact, I think it's everything except for one little topic, which is even more straightforward, and then we're done. Okay. So the very first thing I want to do, you might say, well, could you set F net equals ma? Sure, we could find that maybe this barrier would accelerate because it has different pressures on different sides. So you could do that. An example of what you might do this for, you could build like a potato gun or something out of this. This could be like the inner chamber, or you inflate the pressure to something higher. You put some kind of projectile in there that's airtight so that it maintains the seal. That's why you get a nice kind of wet potato. It makes a pretty decent seal. And then what you do is, of course, once this pressure beats out this pressure, there'll be a significant acceleration, and you can shoot that thing out of there. Okay? But what I'm going to do is introduce a third force, which is gravity. So I'm just going to orient this vertically. And that way we don't have to deal with the thing moving. All I'm going to do is use the force difference that I'm seeing here to hold something up. Okay? So if I have, say, a body of water, like so, and let me earmark some water within the rest. Of course, water is just kind of, is everywhere, so let me pick one particular chunk of water to look at. And we obviously know that this water has weight. If I can find a decent pen, there's got to be one here somewhere. It's getting to be the end of the semester. Didn't quite make it. No. All right, I think that's our best bet. So this water has weight, and yet it doesn't fall down. If I took that chunk of water out and I just put it out in the air here, it would obviously fall and drop. But there it stays perfectly in place. Well, the reason why is, of course, the surrounding water supports it. So there is a lifting force from the water around it, and that must be because the pressure down here is larger than the pressure up here. So basically, the water pressure increases with depth because the water below has to support the water above. The water below has to have all the water above sitting on top of it. So all I'm going to do is now, instead of saying it's the net force, I'm going to say that this force supports the weight of the water. So P1 minus P2 times A supports the weight. Now, I'm playing a little bit fast and loose here. Instead of saying F net equals the force from the fluid in the plus direction minus mg and all that equals 0, I'm just kind of cutting to the chase and saying that the up force and the down force are equal. Okay? All right, so let's see what we can do with this. A is the area, so that's area A here, and I'm going to say that my fluid is a box, so the area that the pressure is pushing on at both the top and the bottom is a common area. Let me give the box a dimension d this way. And let me just start making some substitutions. This is the mass of my chunk of fluid that I'm examining. The mass of my fluid is going to be the density of the fluid times the volume. That's, of course, just definition of density. So mass is density times volume. And then since my volume is a box, a box, length times width times height is this volume, right? Except I already have the length and width in the area. So area times the height, right? So my volume is just A times D. And I'll put that in here. So that's what I have. And then all I'm going to do is simplify. The area cancels. And I get P1 equals P2 plus the density times G times D. I reordered some of the terms for no particular reason. if you're wondering why. But that's basically what I end up with. So I already knew conceptually why pressure 1 had to exceed pressure 2, because the pressure below has to be larger than the pressure above to support this water. And now I can calculate exactly by how much more it is. So P1 is greater than P2 by this amount. So that is simply just from Newton's laws stating that I know that if the chunk of water doesn't fall down, this is how much the pressure at the bottom has to exceed the pressure at the top. Okay? So I'm actually going to apply this in several different ways, one of which is to just get the overall pressure formula, and then also for a barometer. So let's go ahead and do that. The first thing I'm going to do is I'm just going to take the top of that column of water that I just put, and I'm just going to bring it right up to the surface, because I know the pressure there. That's what? Atmospheric, right? If I haven't gone in the water yet, I'm still at atmospheric pressure. So I go ahead and I imagine that my box here, the top of it is right here. So the P1 is PATM. Oh, sorry, I call it P2. And then this distance here, that's actually kind of cool, because that ends up just being my depth under the surface, right? And so this is my P1, which I'm going to call the pressure at depth, okay? So that's ultimately what I'm interested in, is can I find a formula for the pressure underwater? So the formula, if I take my equation and I just plug in, the pressure at a given depth will be the pressure of the atmosphere plus this stuff. So I now have an equation which can calculate what is the pressure at any depth underneath the surface that I want. So if your depth is 0, of course, your pressure is atmospheric. You haven't gone in yet, so you're just sitting out in the atmosphere. And then D is the depth. That's why I picked D, by the way, because I was about to use it for depth. This is going to be the positive distance below the surface that you are. And the more this distance increases, the more the pressure increases from atmospheric pressure. And hopefully that is something you already are well aware of. The deeper you go in a body of water, the more the pressure is. The only other ingredients besides your depth are what fluid are you jumping into, because of course how dense it is depends on how much fluid is sitting above your head at a given depth, right? So if you jump into water and you jump 1 meter down in water, you have 1 meter of water above you, but if you jump into a pool of mercury, which for health reasons I don't recommend, you will have a far more weight of mercury sitting above your head when you're 1 meter deep. Okay, so the density does matter. And then the final ingredient, of course, this whole thing is driven by gravity. You wouldn't have a pressure increase if the water below didn't have to support the water above against gravity. So if you had a big blob of water out in space, you could go down as far into it as you want, and the pressure would still be the same as whatever is on the surface. Gravity is driving the pressure increase. Okay? One thing that does not actually depend on is the area. The area cancels. So you don't have to worry about the width of the column here. And in fact, the column of water that I was using really was kind of a trick in the derivation, but that's not necessary. Okay? So it doesn't really matter the width of water you have above your head, just the height of water above your head. And you probably know that if you can dive down into the bottom of a swimming pool, you can also dive down to the same depth in a lake. It doesn't matter that the width of a lake is different from the width of the swimming pool. Okay? The only thing that matters is how deep you go below in what fluid. And I guess also on what planet, right? So the G matters as well. Okay, so that's called the hydrostatic pressure formula. It'll tell you the pressure at any depth. Okay. And by the way, if you've ever went down to the bottom of a swimming pool, or maybe a little deeper, you might notice your ears hurt, right? So let's talk about why that is. Here is your ear. You have an eardrum, which seals off the air that's in your outer ear that's exposed out to the air with the air that's inside. So you have potentially two different sets of pressures. Now when you jump down, hold your breath and jump in, you've sealed in your atmospheric pressure on the inside, but obviously we know that the pressure outside is significantly increased. So what is going to be the overall direction of force on your eardrum? Toward the lower pressure, exactly. And at some point, this starts to hurt. That's your body's way of telling you you shouldn't do this. And if you keep going, at some point, it's going to burst your eardrum, right? So if you've ever, say, jumped into a swimming pool, at the bottom of a swimming pool, your ears already hurt, you may wonder if scuba divers that go down 2, 3, 4, 5, 6 times like that, do they just have a high pain threshold? No. In fact, at those steps, if you didn't do anything, your eardrum would easily burst. They have a trick up their sleeve, which is called equalization. So they are breathing from a tank on their back. They are capable of breathing normally. And so they have access to breathe in and out normally. So if they don't want to be in pain, what they do is this. They inhale a lung full of air. By the way, in order to make your lungs expand as much as they normally do on the surface, you actually have to have a much larger pressure inside your lungs to inflate against the larger pressure outside. So you're taking in pressurized air. It's a much higher pressure than it would be otherwise, but that's what's necessary to expand your lungs that much under that deep of a pressure. So now you have air in your lungs, then you exhale. But instead of just exhaling out and getting bubbles and stuff like that up, you close your mouth, you close your nose, and then you exhale up into your sinuses. So you push air up through your eustachian tubes, up into your inner ear, and you basically just inflate your own head. So this pressure goes back up, and then the pain goes away. So that's why it's called pressure equalization. There's pressure that's large, but if it's large on both sides, there's no force overall. Okay? So that's how you can do this and dive down to those depths. You can still take advantage of this if you want to, even if, if you try going down to the bottom of a swimming pool, you obviously, if you're not breathing from a tank, you still have some air in your lungs. What you can do is just take a little bit of the air you have and just very gently, don't do it too much, you don't want to blow your eardrum out the other way, okay? Very gently, go like that and you'll get immediate pain relief. Okay? Some people are better at it than others. It really depends on the width of your eustachian tubes. Some people have really narrow tubes and it's hard to push stuff through it. Okay? Also, you definitely don't want to do this when you're kind of phlegmed up, because then your eustachian tubes have mucus in them, and the last thing you want to be doing is pushing mucus up into your inner ear. Okay? So they tell you never to go scuba diving when you're congested. Okay? You can also use this on planes if your ears hurt when you are, for instance, when you're landing. Okay, so if you're landing, you've been up at 30,000 feet for a while. You have a smaller pressure inside your ear because you've been there for a while. You've had a chance to naturally get adjusted, and then you come down to sea level where the pressure is much higher. So if you get pain, then you can use the same trick. So just exhale into your sinuses. Bring this pressure back up to atmospheric pressure. In that case, you're trying to bring them both to atmospheric pressure. It's lower than atmospheric pressure at first because you've been flying up there for a while. A lot of times for people who use station tubes are narrow or clogged up, they do all these things that they recommend all these things, which are basically designed to relax those. Yawning, going like this with your jaw, chewing gum, these are all things that are basically just supposed to open that up a little bit, that passage from your, where you normally take in air to your inner ear. You should definitely not try to do this when you're taking off, okay? Because the problem that when you're taking off is, of course, you have atmospheric pressure inside, and you're going to a lower pressure. So there, if you blew air into your inner ears, you'd make yourself feel worse. Okay. Does that make sense? Okay, so it's all about pressure equalization. Okay. The other thing I wanted to tell you about was that this is one particular example of a way to characterize pressure. Generally speaking, you can characterize total pressure as atmospheric pressure plus an adjustment. In this particular case, our adjustment is this, but this is a more generic idea even than this one, okay? So that adjustment is called gauge pressure, okay? So first of all, let me remind you that pressure is a number. It's a scalar. It's a positive number. There is no such thing as negative overall pressure. The pressure is either 0 or more than 0, okay? So the total pressure is expected to be a positive value, always. And atmospheric pressure, of course, is just one particular value, so that's always positive. However, it is very useful to talk about pressures not as total amounts, but as how are they different from atmospheric pressure. Atmospheric pressure is where we spend all of our time, and if the pressure is that's like our baseline, right? You don't need someone to tell you that's the baseline, everything's fine, okay? What you're more interested in is when the pressure goes up from that or goes down from that, okay? So if you had a pressure gauge, you'd probably want it to read 0 when you're at the beach and you haven't jumped in the water yet. You're just sitting there. Why would you want it to read 100,000 all the time? Okay, which is about atmospheric pressure, 100,000 pascals. Why not just have it say 0, which means everything's fine, and then the pressure can change from there, and that tells you that you're going somewhere other than where you normally live. So in this case, for instance, the pressure is going to increase when we jump in, so we're going to have a positive gauge pressure, which simply means that the total pressure is going to exceed atmospheric pressure. We're going somewhere where the pressure is larger. Okay? But, and not that it can come out of this formula, but in other circumstances, you can use the same idea. There is a possible to have a negative gauge pressure. And that just simply means that the total pressure, which is positive, happens to be less than the atmospheric pressure. So notice it's just the adjustment that is possible to be negative. Okay? So this, you'll hear this all the time. They almost never say gauge pressure. You'll just hear them say positive pressure or negative pressure. Okay? This has applications in healthcare, positive pressure rooms, negative pressure rooms. First of all the pressures are positive. They mean gauge pressure. They mean relative to atmospheric pressure. So if you have a positive gauge pressure room, the total pressure in that room is greater than atmospheric pressure. Can anyone think of why would you want to put a patient into a room with positive gauge pressure or positive gauge pressure? That's right. They don't want anything coming in, right? They want the pressure to be larger in that room, so if anything leaks between that room and the environment, it's going to leak out. So that might be for someone who's immunocompromised. So you don't want all germs getting in from everybody walking by in the hallway, right? So someone immunocompromised should go into a positive pressure room, okay? So if you're, say, placing a patient, just think back to me and think, I should put this person in a positive pressure room because of this, okay? What would be a reason why you want to put a patient into a negative pressure room or negative gauge pressure? They have something contagious, TB, Ebola, something you do not want whatever they have to get out. It's okay if somebody walking by the hallway, maybe their flu germs is sort of okay to get in, but you really don't want whatever they have to get out, okay? So you'll hear this commonly referred, they almost never say the word gauge, but when they say positive and negative pressure, what that means is relative to the normal baseline atmospheric pressure, okay? So this was just an opportunity for me to bring up the concept. In this particular case, of course, the pressure is always going to be larger. So the gauge pressure is always positive, and the deeper you go, the more it will be. So in this particular case, P gauge is rho g d. And by the way, I will point out that if you look at just the gauge pressure, you have all these nice proportionalities available. So for instance, if you double the depth, you'll double the gauge pressure. Okay?